Hey everyone, in this video we're going to talk about section 3.3b, which is about concavity and the second derivative test. So we all know derivatives are so fun, so why stop at one derivative when you can take two? I'll see myself out now. But no, really, the official definition of this, what the second derivative represents on a graph, is the original f's concavity. Now, I like to kind of think about it in terms also of f prime. So if a derivative represents change, the second derivative represents how the first derivative is changing. And we know the first derivative is the slope. So the second derivative also represents how slope, say f prime, is changing. Now, when we're trying to think about the concavity of it, we know that we have two different types of concavity, right? We have concave up and concave down. So the graph is going to be concave up when y prime is increasing or where y double prime is greater than 0. And we're going to be concave down if y prime is decreasing or where y double prime is less than 0, when it's negative. To kind of illustrate this, I'm going to show you two examples. So let's say that we have x squared, right? And we all know what the graph of x squared looks like. Hopefully, at least, by this point, you know what x squared looks like. We know that if we take the derivative, we get 2x. And if we take the derivative of the first derivative, we just get 2, which is a positive number. So in this case, I know that we're concave up because our second derivative is positive. Now, if we're thinking about it in terms of the slope, we're saying that the slope of y prime is increasing all across the domain of x squared. Strap in. Okay, so I know that especially like when we're to the right of 0, when x is 0 or greater, I can definitely see that our slopes are increasing, right? Positive slope, positive slope, positive slope. Now, on the other side, you're probably like, well, Ms. Dolence, we got negative slopes over here. But if we're thinking about how the slope is changing, not necessarily the sign of the slope, we're saying that the slope is getting bigger. So if I'm looking at like this slope right here, it's pretty negative. And then if I look at the slope right kind of to the right of it, it's negative, but it's slightly less negative. And if I look at this one, okay, we get a little less negative, and eventually it becomes 0. So our slopes are increasing. Yeah, they're negative, but they're getting bigger and bigger. Then when we switch over, okay, I have a slightly bigger slope than 0, and now my slope is slightly bigger than that, slightly bigger. So that's where we see how the slope is changing, or where f prime is changing. Same thing, let's look at negative x squared. So I know if I take the derivative, I get negative 2x, and if I take the derivative of that, I get negative 2. And so the graph of this is just going to be flipped over the x-axis. So in this case, we are saying that our slopes are going to be getting more and more and more negative. So here, okay, we have a positive slope. Here, we still have a positive slope, slightly less positive though, slightly less positive, and now it's 0. And now it's negative, now it's kind of a bigger negative number, and now it's even more negative, and so that's how we can tell if it's concave down. So just like how we could tell where the function was increasing or decreasing based on the first derivative, we can tell where a function's concave up or concave down based off of the second derivative. Now, we are going to be looking for not critical values. Remember, that's where our first derivative was equal to 0. We're going to be looking for inflection points. And inflection points are where the concavity changes sign. So if we can identify where that occurs, well, we know where we change from concave up to concave down. And the way we're going to find our inflection points is going to be similar to finding a critical value. We're going to determine where the second derivative is undefined or equal to 0. We're going to make a sign chart. And then we're going to determine if we really do switch signs from the second derivative. Okay, we're going to take a pause for a second. My dog is about to bark for food, so hold on, it's dinner time. All right, he runs the household. Okay, example 1, we're going to find all of the inflection points for the function. Looks like we have y equals x to the 1/3 power times the quantity x minus 4. Whew. Okay, so I know that if we're finding points of inflection, that means that our eventual answer does need to be an xy coordinate pair. Okay, so we'll just keep that in mind. Okay, I know that we are going to need to have a second derivative, and I know that I could product rule this because I do have two functions multiplied together. However, I feel like the product rule when we do second derivative, we're going to have a lot of stuff going on. Let's go ahead and just distribute this through, and then we don't have to do that. So let's see, we're going to have x to the 1/3 times x, that's going to be 4/3 power, and then this will be minus 4x to the 1/3. Okay, so now that we have this, let's go ahead and take our first derivative. So y prime is going to be equal to 4/3 x to the 1/3 power minus, let's see, bring down that 1/3, we'll have 4/3 x to the negative 2/3 power. Okay, so there's our first derivative. Since this is inflection points, we need a second derivative. So y double prime. We need to take the derivative one more time. So let's see, we're going to have 4/9 x to the negative 2/3 power minus, let's see, that's actually become plus 8/9 x to the negative 5/3 power. Jeez, okay. Let's go ahead and, I don't know if it's going to be easy to do this. Let's factor out our greatest common factor. I think we're going to have a 4/9 x to the negative 2/3 in common between all of this. So that's going to leave us with 1 plus 2x negative 3/3, so negative 1. Okay, and then I don't even know if this is necessary. I'm going to clean it up a little, just get rid of or satisfy our negative exponents. Perfect, we're doing great. Okay, so here is our second derivative, and so now we need to find we're trying to find potential inflection points. So let's call our potential inflection points, let's call these pips. Okay, we're going to find our pips. We're going to do that by figuring out where y double prime is equal to 0 and where y double prime is undefined. Okay, so this is going to be equal to 0, so we're going to have 4/9 x to the 2/3, 1 plus 2 over x equals 0. Okay, so that's like a zero product property, so let's set both parts of this equal to 0. I don't need a parenthesis. Okay, well, looking at this first part here, well, this is never equal to 0, so we're not going to get any pips here. Looking at the second part, though, if I were to, let's subtract that 1 over, so we have 2 over x equals negative 1. Well, this is going to be true when x is equal to negative 2. So we have our first pip, everyone. X equals negative 2. Okay, next thing that we're looking at is values of x that's going to make y double prime undefined. And in this case, I think it's just easiest to kind of look at our denominators and think, what can't we plug in that's going to make that, make the denominator be equal to 0? And I actually think in both cases here, it's going to be 0. So we get our second pip of x equals 0. Okay, so now that we have our potential inflection points, our pips, let's go ahead and make a sign chart. I'm going to be pros at sign charts by the end of this. Okay, let's find some test values. I like -3, -1, and 1. Okay, so if we plug in -3, to our second derivative, let's see what we get. Well, plugging it in here is going to, because this is x squared, the cube root. So, okay, so that's going to make that positive. And then plugging this in, we'll have 1 plus negative 2/3. That's going to be positive. Okay, so this interval here is positive. So what that means is that we are concave up on this interval. Plugging in -1, okay, so the first part here, it's going to give us a positive number. The second portion, though, it's going to give us a negative. So we are, y double prime is negative on this interval. We are concave down. And then plugging in 1 for both parts for x, it's going to give us a positive number as well. So we do switch back to concave up. So I see here that our concavity changes in two different places. We change at -2 and we change at 0. So remember, the question is asking us to find all points of inflection. So we found the x values. Now we need to plug them in and find our y values. So I want to know what y of 0 is and what y of -2 is. And you can go ahead, take a second, try this out with your calculator. I got y of 0 is equal to 0, and y of negative 2 is 6 cubed root of 2. Now, if you got something different, please let me know, and I can go ahead and change this. Okay, so let's justify our answer. It didn't tell us to justify, but we're going to do it anyways. Okay, so we're going to say that we have points of inflection, POIs, at the point negative 2, 6 cube root of 2, and 0, 0. And we're going to explain how we know. Well, it's because just our definition of a point of inflection, y double prime changes sign at those points. All right, so that is that example. In this case, this was just asking us to find points of inflection. Let's flip over to our next page. We had a first derivative test for helping us find local extrema, so we also have a second derivative test to help us find local extrema. Extrema, remember that means mins and maxes. So, okay, let's say that we have a point C. Here's our point, C. And at that point, we have a horizontal tangent, meaning that our first derivative is 0. Well, okay, if the second derivative at that point is negative, then our function is concave down, so meaning that that point, C, is a local maximum. Or, okay, here's another point, C. We have our horizontal tangent. Let's say that the second derivative there is positive. Well, then we're concave up. So the second derivative test uses the concavity to tell us where mins and maxes are. All right, okay, well, let's say at C, our second derivative is 0, or if it's undefined, then the second derivative test is going to be inconclusive. So if that happens, then we're going to have to revert back to the first derivative test to check what's happening at that point. Okay, we're going to look at our first example using the second derivative test to find local extreme values. On example 1, it's kind of a lot of writing, so you might want to write small, just as a heads up. So we have a function y equals x cubed plus 3x squared minus 2. Since we're trying to find extreme values, we're going to start this off the same way that we would start off the first derivative test. So we need to check 3 things. Endpoints, where the first derivative is 0, and where the first derivative doesn't exist. Okay, in example 1, we don't have any endpoints because we don't have a specified domain, so that takes us out. And so now, okay, let's find our first derivative. So first derivative, that's going to be 3x squared plus 6x. Okay, this is a polynomial. Polynomials are going to exist everywhere, so there's no place that the first derivative does not exist. So, okay, we're still going to find our critical values because I need to have those candidates for where our mins and maxes are. So let's set our first derivative equal to 0. 3x squared plus 6x equals 0. I'm going to factor out, let's see, a 3x. So that's going to leave me with x plus 2 equals 0. And then zero product property, we can set each of these equal to 0. So it looks like our critical values, we have x equals 0 and x equals negative 2. So I'm going to write that down. So we have 2 potential candidates where this could happen. Okay, so now here's the deal. We have places where we could have mins and maxes. Let's find our second derivative and check to see what our sign of our second derivative is. So we need to find y double prime. Well, that's going to be 6x plus 6. So I'm going to take my critical values and I'm going to plug them in here. So y double prime of, let's do negative 2 first. Plugging that in, okay, that would be negative 12 plus 6. That's going to be negative 6. And I'm not super concerned with what the actual value is. What I'm really concerned about is that this is negative. Let's see. So since it's negative, I know that that means that our function is concave down. Neat. Okay, well that means that we're going to have a local maximum according to the second derivative test. And okay, now checking our critical value of 0, plugging that into the second derivative, 0 plus 6, that's a 6. It's positive, so that means that at that point we are concave up. So both of our critical values end up being extreme values. So we need to say we have a local max of something. We know that it occurs at 0, and then we're going to justify it. So we actually need to figure out where our mins and our maxes are. So we're just going to take our confirmed extreme values, plug it into the original function. So let's see. So y of 0, that's going to be -2. And y of -2, let's see, 2. Sounds about right. Okay. So now let's state what we found. So there is a local max of 2. So that was this value, right? And that occurred at x equals -2. And now let's state why. So we knew first because we found this value because y prime of -2 is equal to 0. And we knew that y double prime of -2 is negative. Now let's do the same thing for our local min. So now we have a local min, and that was -2. So that was this point here. We knew that occurred at x equals 0, and we knew this because, okay, y prime of 0 is equal to 0. That's where we found our critical value. And our second derivative at 0 is positive. So we're using our second derivative test to justify it. So notice that we mentioned two things. We mentioned how we determined where those critical values were. That was using the first derivative. And we mentioned the second derivative, and we mentioned its sign. Okay, we're going to look at example 2, so let's draw ourselves a little line. Hopefully that didn't take up too much space. It happens though. Okay, you're going to do the same steps as we did in example 1. We just have a slightly harder function. So I'm going to encourage you to pause the video and to try this on your own. I'll put up my work. We can check ourselves. But yeah, pause the video, try it out. Let's see how we do. All right, hopefully you've had some time. You tried it out yourself. So I'm going to talk you through what I did. First thing I did was I found our critical values. I used the product rule to help me find y prime. I did some algebraic manipulation. I simplified my first derivative because I knew I was going to have to use it, right? I knew I was going to have to find it, find critical values from it. It's going to be easier to do simplifying. So I got e to the -x times -x plus 1. I knew that this was never going to be 0. Really, this was 1 over e equals 0. That's never going to happen. And so I got one critical value of x equals 1. I knew I didn't have to check any endpoints because we weren't given a domain. And I knew that our first derivative was never going to be undefined anywhere. So then once I had my critical value, knowing I had to use the second derivative test, well, it's helpful to have our second derivative. So I found that. Again, I used my simplified first derivative. So that was another product rule. I did some algebraic manipulation to get it into a nice form again. I took my critical value of 1 and I evaluated my second derivative with it. And I saw that the second derivative at that point was a negative number. So because it was negative, that meant that we were concave down. So that meant I knew that I had a local maximum there. Well, okay, cool. So our critical value does end up being an extreme value. So we actually have to figure out what the maximum value is. So we can take that extreme value 1, we put it back into our just original function. So when x is 1, y is 1 over e. And so I justified it. So we had a local max of 1 over e at x equals 1. And then I mentioned two things. I mentioned the first derivative, which is how I found that critical value. And then I mentioned the second derivative, and I mentioned how I knew it was going to be a local max. Since it was negative, I know it's concave down. That's how we got our local max. Okay, hopefully we did okay. If you have any questions, you can ask me next time you see me.